Okay, so welcome to this video that I'm going to do very quick. This is in order to check the model solution compared to the static solution. So I already created the models. Let's open this one. And basically here, this is very simple. This is a plate that you see is 15. This is the boundary condition, but it is it is 1500 millimeters by 500 millimeters. I just did a surface. You create the mesh. I think each one is 25 or 50 millimeters. And I'm just going to open here very quick. Material properties are over here. Okay, so this is the Young modulus, the new, and we need the mass density, but I will show it later on. Okay, so we don't need it for the static analysis. So over here, the properties, we only have plates. This is a strange thickness. This is in millimeters, but you will see, you will understand once we go to a future example, not on this video, but this is just in support of one of the following videos for a stiffened panel. So, okay. And the load over here is a uniform pressure of 0.05, okay? So this is a 1500. We can go here, eliminate the tools, works. So now this is the deformation. I already run the program. But if we come here, you should see the loading, 0.05 pointing down. And the boundary condition actually simply supported or pinned, but I decided to create them that way because I have a better control, okay? So the type of solution over here, I just run the static analysis, nothing special, and we look at the results. So here we're gonna look at the total translation. Okay, so its total translation will be 16.96. All right, under this shape, is deformed under this shape. This is important, okay, that you see this is like a quarter of a sine wave, okay, or a sine wave from here to here. So this is the formation. We're also going to look at the stress on the x direction, which is about 74.08. This means in compression. And the y over here is about 186.1. Okay. All right, so we can assume, let's take this is our exact solution. So let me just save. Now what we're going to do is, before solving, let me just look at this program here to try to understand what's happening on the model solution. So basically it's the same model as before, but maybe here I need to add same properties, but this will be the density, okay, of the aluminum. Okay. So basically if we run the modes analysis, not this one, so this one here, this one, we could delete it in this page. It's not going to be needed. Okay, so if you come here, manage, you go next, edit. You don't need to change anything here. Okay, you just need to solve it. The thing you can specify here, but it's 36. I think the default is 10, but you can put anything you want. Okay, so done, and you can click analysis. We already run. So basically what we see here is that this will be the first mode that happens at 7.518 Hertz. So this will be the first shape of the formation. Okay. This will be the shape of the formation, 2 sound waves over here, 1 in that direction. So this is called the mode 2, 1. This one is called the mode 1, 1. This one is called the mode what? 3, 1. Okay, let's do one more. This one would be called what? 1, 2, 3, 4, 1, and so on and so on. So the idea behind the modal analysis is, let's say, okay, our structure subjected to the uniform pressure, okay, is going to deform more under which shape? Probably is going to be this one. You look at this one. What is the shape of this one? The static solution is that one over here. Okay. So in order to set up this problem, we already run these ones. You don't really have to, but it helps to run this analysis first. I already did this, file open. So this is here, we are just solving for mode. Okay, what am I doing here? That's not the one I want. Open. Okay, so this is one that I want here. But this one I think is for the formal. So let's first run the solution, like if we only take the first mode over here, which is the 7 point something. This is a static solution, okay? So we come here, let me modify this one. Let's do file, save as, and I will modify one mode, save, yes. Okay, so, and let me delete all this stuff over here. All right, so here I need to come to model, load, dynamic analysis, and here probably number of modes 1, just the first one out of the list. Okay. And now just to double check, you should not change this, but why not making sure that the program is doing exactly what we want? Come over here and you just make sure to put 1. And then by default, you can, this is not going to change anything in this case. Make sure that it's also going to calculate the stresses, okay, which here is not defined. Okay. And you click analyze. Everything else is exactly the same. Not really. I just, you need to do one more thing on the model because it's transient. So the load is unchanged. Okay. But we did create a function over here. All this is created after the processing. So basically I just created here a function that is 0, that is 1 at 0, and after 10 seconds it's still 1. So this is constant. And the value over here, and this function is used to define the load over here. So basically what I'm saying is that the load here, you see function of pressure, is 0.05 between the 10 seconds and is uniform. So now when I come here and select on the analysis, the transient analysis, okay, the load would be transient, but would be all the time equal to negative 0.05. So I do this all the time. You don't have to. You run it. It should be pretty quick. Okay, this is already creating the output. All right, let me close this. And maybe let's keep this one here. We go here to post-processing. No, sharding over here. So I already did this, but just to try to do it, maybe let me just delete it. Delete all. Okay. Okay, so new data series. So let's see here, we're going to look at versus data set. You could just do it versus entity, but I think you will see why. absolute value. We're going to look at the total translation, and the location will be the center, which should be the maximum. So I think should be like right here, okay, 750 and 250, and from the corners looks to be over there, okay? So we click OK. Okay, and over here you see that what happens after certain time, after almost, say after 3 seconds or 2 seconds is constant, and this value will be equal to the final value. Can find this one here, we can do cancel, done. Okay, and we see this one deformation we're gonna get. Let's look at the last one, a deformation of 18.69, okay? Which is not what we're looking for, 19.96, all right? But basically just using one mode, the mode of this shape over here, or let me just open this one. By just using the mode of this frequency here, 7.51, by just using this shape, we're able to approximate to 18.69 as compared to 16.96, okay? So now we do the same thing here for the model, but this time we're gonna use 2. So if I open, so this one is already set up. So this time we'll be using which mode? So let's see on the analysis which one I'm using. So model, load, dynamic analysis, it says I'm using 3. But if I'm using 3 modes, what would be those 3 modes? Will be mode 1, 1, mode 2, 1, that actually will have no contribution because it's symmetric. I will explain now why it's 0, okay? But so 1, 1, 2, 1, and sorry, 1, 2, and 3, 1. All right. So already did. Okay, so this will be the solution for 1, 1 and 3, 1. So basically two modes only, okay? About 3 because we use the first 3, but the second one will have no contribution. I will explain that in a minute. So on the analysis, here is a transient, manage. You don't have to change that, but I know I like to do it just to make sure. Same as before, but probably I just put over here 3, okay, instead of 1. And everything else, let's check that we also have the stress. No, it wasn't there. So stress for model, okay. Done. We should have already the results over here. And as before, we could do the figure. Maybe it's already done. And now you see, now we went to what? To 16 point something. So before with one mode, we had 18 point something. Now with those 2 modes, 1, 1 and 3, 1, we move down to 17 onto the line of 17. So 16 point something. So again, if we go to the last step, 16.76 using those 2 modes. Using one mode, we are at 18.69. And if you want the exact solution, is about 16.96. So you see that 2 modes is already pretty close. All right. So now let's go to the important part, which is the one I like to do, the validation. So this is from, I'm not going to go in detail, but this is from Timoshenko. Basically, this is the dimensions of the plate, the thickness, the Poisson ratio, the models of the elasticity, and the density. Okay, I don't know why I have it twice. I already did it. The location is the middle of the plate where it's maximum. This is the load, 0.05. Again, this is from the book. Again, location of the stresses at the middle, because I'm asked to find the stresses at different locations. So initially the stress is 0, deformation is 0. And here what I do is add each one of the modes. So you see here, everything is in function of sine and sine. So If you have two signs, what would that be? Let's see. Let me go back to here. So we have two signs, frequencies, like this one. Okay, if you integrate from here to here, what will be the total contribution? Plus this over here minus this one, so it will be 0. Okay, this one you will have the contribution of this one because it's a sign function. This one will have 1 negative, 2 negative, 1 positive, so we'll have a contribution of 1. This one, 1, 2, 3, 4, they cancel each other. So all the even modes will cancel each other. Okay, so basically this is what this is showing over here. All right, so basically I put 4 modes, but you can really solve for as many as you want. So here's just for 1. See, just m equal 1, n equal 1. You go through all this stuff, run it. And what do I get? Deformation 18.6971. Let me remove this. So for one mode, 18.6971. 18.69. Okay, very close. F5. Describe. Okay, X first. We get here 91.67. We can get closer if we refine the mesh, 92.166, but good enough. And if we do the Y, F5, deform, Y, okay, okay. We get 215.4. Here I get 216.6, okay? So again, this is just a solution for one mode, but that doesn't mean it's the exact solution. The exact solution probably is more closer to this one, okay? So you look 16.96, and the Y is about 186, and this one is given us here 215, so it's quite a difference. Now the 1.3 is getting a bit closer, probably. This is the 1.3 modes, and here we had what, the 16.76, F5. If we do the, oops, you see, we probably need to run again, so we get the stresses. All right, so it looks like I forgot to put the stresses before. Preserve and do. Okay, so here, manage, edit. Let's make sure we have the stresses. This is by the end. Okay, stresses. Okay, analyze. Probably now we can remove. Now we can leave here. All right, so again, we're gonna do the figure. Okay, so it's done for us. So this will be just for the deformation, 16.96. We come here, deform. Okay, so let's do this one. This will always give us the 16.76. And this is gonna give us now the 84.94. All right. And we could plot here the same thing, but we don't really need it. If we look at the last value, all right, because we will have converged. If you want to put it here, maybe what you could do is this, if you really want to do it. Okay, let's put here new. Instead of new translation, can put top XY. Let's set location. Again, we're going to use the 1750. Looks like it's somewhere over here. And okay. And oops, oh, we put the total translation, sorry. XY normal, okay. So now, I don't know what happened here. Okay, I don't know what's happening here, but let's see. Oh, it's trying to show both of them at the same time. So that's not I will redo it from scratch. But basically, let's look at the top X normal is minus 84 for mode 1, 1, and 3, 1. And the XY and the XY, sorry, and the Y is the 188. Okay, so if you look at this program here, you can do one mode, and this is what we got. All right. Now I could put here, from modes 1 through 3. So this means we'll do 1 and 3 and n equal 1. So this should give us the answer for the 1 and 3. So 1, 1, and 3, 1. So we get, so you see, first one for first mode only is 18.6971. Taking the contribution of 3, 1 is 16.7735. So the total is 7735, okay? And the stresses will go from 63, 57, 54 to 188. And this should compare well. So let's see, this should compare well with this one here, which is here you see the 188.2. We had 188.012 for the Y. And now for the X, we had something strange, 84.94. Oh, but that's the red. We need to look here right in the middle at this node here. So that's maybe important here that we do that now. So, okay, let's do a figure. Let's come here, delete all, okay. And let's do just the X. So 1, let's set, output set. Want to look at the X. All right. Location again will be here. Also, this is the plate because we look at the plate. So let's say we come, will be the middle right here. So here, let's do some multiple ones. This one, this one, this one, and this one. Okay. So they should give more or less the same, but okay. So here you see they give us about 60 something. Okay, so probably 63.57. All right. And if we go here and let's say we take the Y, let's say we put on the same sketch. Yeah, you see we put it on the 186. And if we put on the same figure, the total translation, it will give us here what probably the, I don't remember the value, okay, this is the one at the element, so we cannot compare, we need to look at the node. So forget about this one here. Forget about this line over here, but basically this would be for the stresses. And again, we have the 188.63. Maybe one way to do this in a different way would be to create a group, which looks like I already did, which is just this for elements. So you see here, the X will be 63.21 as compared to 63.57. And okay, let's go check the other ones. And the Y will be 187 compared to the 188. And F5, the total translation would be 16.76 as compared to 16.77, okay, for 1, 1, and 3, 1. And we had the MATLAB that summarized the results on an Excel page. So for example, the contribution of mode 1.1 is 18.697 for the deformation. 1.3 is negative 0.093. We didn't do this one. 3.1 is minus 1.924. So basically, when we did the study now, we selected this one and this one. So when I put them together, you will get 18.697 minus 1.924, and we get the 16.774. And you see the same thing for the stresses. My X, we have this one minus this value. We give it this one over here. And we have this compared to this. And if we compare this, so let's assume this is the perfect solution. This gives us over here 16.96. Okay, so let's put here static solution 16.96. So what I'm trying to do is this over here, okay? 16.96. Then the XY, oops, the Y, we already have that one, will be, but we need the value in the middle. So let me just do this, if you don't mind. F5, we know it's over here. Criteria, okay. So 186.07. So will be 186.07. And the other one will be F5 X normal 68.995. Okay, so let's say 68.995. Okay, so let's say this will be the exact solution. So you see that only 2 modes is very good for the deformation. For the stresses, what would that give us? So we'll do, let's see, we can do this, see if it would work. For the stresses, no. So here what I want to do is basically C2 plus C4 will give us what, 63 as compared to 68. And this one here will be D2 plus D4 will be 188 compared to 186. But again, the more of these values you take, so if we take 1, 1, 1, 3, 3, 1, 3, 3, and so on, we get much better results. And it's a bit tedious to do it on the finite element. But if we come here to the MATLAB code, for example, here I can just put here 1, 2, 3. And let's say this one will be also 1, 2, 3. Okay, but let's go to 11 and 11. So that's a lot of modes. And we should get a lot closer to the exact values. Okay, so in this case, what do we get? We get 16.96 as compared to the exact solution, which is 16.96. So that's exactly the same. For stresses, oops, let's see what happened here. There we go. Okay, so all right, so 16.96, 16.96, 68.995, 68.8037, 186.07, 186.6947. Okay, and again, if you take a lot more modes, you should get very, very, very close to the exact solution that we assume in this case is the static one. All right, so again, this is very important, but this video will be very useful once we go and study the stiffened panel for the validation. Thank you for your time.